Welcome to today's class. Uh, Today's class is going to be somewhat indirectly related to fundamental domains, in the sense that today we are not really going to prove anything about them, but rather the results that we're going to establish today are going to allow us to prove some geometric properties of locally finite fundamental domains next class. We're going to have two main results today, one of an algebraic flavor and the other one of a more analytic flavor. On the algebraic side, we're going to show that if we are given a Fuchsian group and a point in H bar, then the stabilizer in the Fuchsian group of that point in H bar is always cyclic. Right? I mean, the stabilizer, when we consider, of course, the action of the Fuchsian group on H bar by Morris transformations. And on the analytic side, we're going to show that if we are given a discrete subgroup of SL2R with the property of containing a matrix defining a horizontal translation, then there exists a constant, a positive constant, satisfying that for every matrix not in the stabilizer of infinity, of the fixed point of this parabolic transformation, the certain entry of that matrix is is bounded from below by this constant that we're going to show exists. So I mean, notice that in such a group, the elements in the stabilizer of infinity, they all have this matrix equal to 0. So somehow what this lemma says is that every element, every matrix here has either this equal to 0 or bounded from below by a positive constant, so that somehow this 0 is never an accumulation point. When we kind of restrict our attention to this real parameter. Okay, so let us start. So let's get points in H out of the way. That is, suppose that we are giving our Fuchsian group gamma and take a point Z0 in H. So we are taking Z0 in H. Then the stabilizer, this one, the stabilizer of Z0 in gamma, it could be only the identity, right? I mean, it could be it could contain only the identity Morris transformation, or if it contains other transformations, they are all, of course, elliptic with Z0 as fixed point, and so they all have the same fixed point in H bar, right? And as we saw, that implies that they all commute. So this group, this stabilizer, is always abelian for Z0 in H. Right? Okay, so it's an abelian subgroup of gamma, hence cyclic, right? We had already established that every abelian subgroup of a Fuchsian group is necessarily abelian. So it's abelian. So it's and all its non-identity elements are elliptic. So it's actually finite cyclic, right? Okay, so actually the points in H are kind of the easy ones, right? So that actually, what we have shown, and it's kind of the reasoning is as you can see is quite easy to follow. Uh, uh, for every point in H, the stabilizer is finite cyclic. Okay, so now with the points in H out of the way, let us focus on the points in R bar, right? In the circle at infinity of the hyperbolic plane. So let's start. So take such a point, and suppose that that point is fixed by some parabolic element. Then let's show that that the stabilizer in gamma is cyclic. Okay, so suppose take nu parabolic with z naught as fixed point, and then of course without loss of generality we can assume that that point that z naught is infinity, and I mean without loss of generality because take any element of PSL2R. Taking z naught to infinity, and conjugate the whole of gamma by that element taking z naught to infinity. So what we obtain is a subgroup of PSL2R conjugate to gamma, and so that conjugate subgroup is discrete as well. And if the lemma is true for that conjugate of gamma, then it is true for gamma as well, right? And for z naught as well. So let us assume that. Okay, and then you see then and represent nu the parabolic transformation fixing it, represent it. As a matrix with this zero entry and this in SL2R, so we can actually assume we can put it, with ones in the diagonal. Okay, now take any non-identity element of the stabilizer of Z naught, right? So Z naught is infinity. So for any Mobius transformation fixing it, whenever we represent it using a matrix, we know that the lower left entry has to be equal to 0 because it fixes infinity. It fixes infinity, right? Okay. And so we would like to show that B is parabolic. We would like to show that because then the set of fixed points of this transformation would be exactly equal to the set of fixed points of nu, and so they would be forced, they would commute necessarily. And then I keep going. Because then the stabilizer would be abelian and cyclic, which is what I want to show. Right? So I would like to show that this transformation is parabolic, but suppose not. Suppose it's hyperbolic, right? It has to be hyperbolic because it already has a fixed point in R bar, right? So if it has two fixed points, then the other point has to be in R bar and it has to be hyperbolic. Okay. Okay, it's hyperbolic, and then again, then now take an element of PSL2R, fixing infinity, and sending the other fixed point of sigma to 0. I leave you as an exercise to show that such a Mobius transformation in PSL2R exists, and conjugate the group with that Mobius transformation, so that now you obtain a further conjugate of gamma with the property that this nu fixes infinity, and this other sigma that we took in the stabilizer of Z naught is hyperbolic and fixes zero, so that this entry has to be equal to zero. Okay, and then let's play around, right? So let's take A and conjugate it with this other matrix. So here is the computation, and notice since sigma was assumed to be different from the identity. Notice that once we assume that B is different from zero, the A has to be different from 1 or minus 1. Otherwise sigma would be the identity. Okay, which means that here you see the absolute value of this number is really different from the absolute value of A. And replacing B with B inverse if necessary, we can actually assume that the absolute value of A is less than 1, which then means that, see, when we took this matrix, which is an element of pi inverse of gamma, where pi is the projection from SL2R to PSL2R, and conjugated with this matrix, somehow we obtain almost the same matrix, but this upper right entry is multiplied with A squared. So when we conjugate again, it would be get multiplied again with A squared, so it would be A to the fourth times theta, etc. And so inductively, we would have that this conjugation is equal to this. Right? But see, A, we took it to have an absolute value less than 1 without loss of generality. So this converges to the identity, and all of these are elements of this discrete group, right? I mean, gamma is discrete because G was discrete, so this one is a discrete subgroup of SL2R. So you see, we have a sequence in this discrete group that accumulates in the identity. So, but this, I mean, that's precisely the negation of the definition of discreteness. Right? So this assumption must be wrong, and so the only possibility left is that sigma be parabolic. Okay? So what we have proved is then that all elements in this group, in this stabilizer, commute with nu, because all of them have precisely this set as a set of fixed points, right? So they all commute. So the subgroup is abelian, hence discrete. Hence cyclic. Hence cyclic. Okay, and that finishes the proof of the lemma. Okay, so what we have just shown is that when you take a Fuchsian group and take an element of R bar, if for that element of R bar it so happens that its stabilizer contains a parabolic element, then all non-identity elements of that stabilizer are parabolic. That's what we have just shown. Okay, so now let's show that if we take our element of R bar and its stabilizer um, happens to have a hyperbolic element, then all non-identity elements are hyperbolic. Mhm. Uh, and this of course will allow us to show to conclude that the stabilizer is fixed. Okay, so take a hyperbolic element of gamma, fixing our point. Again, conjugating gamma with some Morris transformation in PSL2R is necessary. We can assume that that the fixed point of this hyperbolic element we took is zero. Sorry, is infinity. It's infinity. Uh-huh. And that the fixed points of nu are precisely zero and infinity, right? I mean, again, take the two fixed points of nu, which lie in R bar, and take a Morris transformation in PSL2R, moving one of them to infinity and the other one to zero, and conjugate the whole group gamma by that Morris transformation. Discreteness is preserved. Uh-huh. Algebraic properties are preserved, types are preserved, so on. So it's enough to show it, to prove the lemma under these assumptions. Okay, these two assumptions imply that when I represent my Morris transformation, my hyperbolic Morris transformation with a matrix, I can assert that the matrix has a certain specific shape or form. And actually here I can assume that with alpha positive, right? Okay, and now take a non-identity element of the stabilizer. Mm-hmm. You see, it's in the stabilizer of Z naught. A priori, we wouldn't even know whether it fixes or not any other point in R bar different from Z naught. Right? In particular, a priori, we wouldn't know whether sigma fixes zero or not. Right? We only know that it fixes infinity. Mm-hmm. Okay, but it fixes infinity, so we can represent it this way as a matrix with this lower left entry being equal to zero. Mm-hmm. Okay, so represent it. Now something that by now we can make sure is that since nu is hyperbolic, sigma cannot be parabolic, right? Because if it were parabolic, then by the previous lemma, nu would be forced to be parabolic. Anyway, so this we can say, so that it's not that sigma is not parabolic. So okay, so at least there's at least a different sigma has at least another fixed point different from Z naught. But right now we don't know whether this other fixed point of sigma is zero or not. And that's what we want to prove, that the fixed points of sigma are precisely infinity and zero. Right now, we only know that sigma fixes infinity. Okay, so let's do some computation. So see, we want to show that sigma fixes zero. So we want to show that B is equal to zero. Suppose not. Suppose B is not zero. Okay, and then let's do some computation. And this time, instead of conjugating A with B as before, now we conjugate B with A. Okay, so here is the computation. And so you see what we obtain is this, right? So inductively we have this, and then replacing replacing nu with nu inverse, which would again be hyperbolic and would have the same fixed points if necessary. Right? Replacing nu with its inverse if necessary, we could assume that that the absolute value of alpha is less than 1, and so you see this would be a sequence of elements of pi inverse of gamma converging to A00A inverse, right? In SL2R, right? But then this one accumulates in SL2R, and we showed that if it's a discrete subgroup, it cannot accumulate in SL2R. So what must happen? That this assumption must be wrong. So we can conclude that B is 0, but then we are done, right? Because then sigma then obviously fixes 0, and we conclude this. So what we conclude from this is that all non-identity elements of the stabilizer of Z0 commute with nu. So the stabilizer is an abelian subgroup of our Fuchsian group gamma, which means that it has to be cyclic. And this finishes the proof of the first result. So let me write it as a theorem gamma Fuchsian of course gamma in PSL2R implies that every element of H has cyclic stabilized, and actually of H bar, right? So, okay. Now let's move on to the kind of analytic flavor result. So as I said at the beginning of the class, we're going to show that if you give me a discrete subgroup of SL2R containing some non-identity, some matrix defining a Mobius transformation, which is a horizontal translation, so that you see for this matrix in G, the associated Mobius transformation has infinity as only fixed point. Then there is some positive constant with the property that for every element of G, either the lower left entry is 0 or bounded from below by this constant in absolute value, right? When we consider, in particular, when we consider this set, gamma, for which there exists B in for which there exists a matrix alpha, beta, gamma, delta in G. I mean, with gamma as the lower left entry, right? This one does not accumulate in 0. That's what this lemma says, or it can be interpreted that way. Okay, so as you can see, the proof is a bit long. It's somewhat technical. Okay, so let's start taking the Fuchsian subgroup in PSL2R I mean, the Mobius transformations defined by the elements of G, by the matrices in G. We know that at least one element of gamma, namely this mu A, is at least one of those points is parabolic with infinity as fixed point. So this set is infinite cyclic, let's say by the previous result, by this theorem. So let us write it as generated by someone with this someone, right? I mean, this someone can actually, maybe it's not the original we took here, but we can replace the original one in the statement with a generator of this cyclic group. And then replacing with the inverse is necessary. We can assume that beta is positive. Okay. Now suppose that you see that this is not that this accumulates in zero, so that that this constant doesn't exist, so that whenever you give me such C, one can find an element here where one has this inequality, right? And then taking this, the constant 1 over n, one can form a sequence of elements of G with the property that the sequence formed by the lower left entries converges to 0. Okay, converges to 0, and also you see, kind of take all of them. It accumulates, right, in 0. So in all of them, one can take this different from 0, so that it doesn't fix infinity. Okay. Now replacing G with pi inverse of gamma, which is again discrete and contains G, replacing it if necessary, and you multiplying every matrix, each of these matrices with -1 if necessary. Again, we can assume that all these entries are actually positive, right? Yeah, sorry, and here maybe I should just say, yeah, sorry, all of them are positive. Okay. Okay. So it's multiplying with -1, right? So when I multiply an element of G with -1, maybe I don't land in G, but I do land in this discrete subgroup. It is discrete because gamma is discrete, and gamma is discrete because G was discrete, right? This we showed at some point. Okay, so that I am going to assume. So it's the gamma n's form a sequence of positive real numbers converging to 0. So this sequence is non-stationary, right? And I can actually assume that they are all different, right? By extracting a subsequence if necessary, right? So if necessary, I am actually going to assume that all of these are different. Okay. Right. So now let's do some computation, right? I'm going to compose with certain matrices defining a horizontal translation. Okay. So take an, right, and compose it. Multiply it with this a to the k, a to the l, right? Do the computation. You get here, right? And you see somehow the funny thing is that the lower left entry of this one is gamma n, right? The same one as a n. So this multiplication, it of course affects the matrix, but funnily enough, it doesn't affect this lower left entry. All right. Now, for each n, take integers. Let's say take kn, an integer kn, satisfying these two inequalities. So somehow it really is consider consider the real number beta gamma n, and consider all the real numbers obtained by adding to alpha n minus 1 the integral multiples of this same real number. Then, since beta and gamma n are positive, of course, you know, this sequence this sequence is kind of goes like step by step, and there is one point where it is below, but in the next step you surpass it, right? So there is actually exactly one integer kn satisfying both of these inequalities. By the way, notice that this inequality also means that you know, when you cancel this one, what happens is that kn times beta gamma n then plus alpha n is greater than 1. That is yeah, okay. Okay, and likewise, when you consider now all the real numbers obtained by adding to dn minus 1 the integral multiples again of beta gamma n, there is exactly one integer ln satisfying both of these, right? Okay, so such integers exists. Okay, so we take them, and now we are going to take this product for those choices of integers, right? And let's write bn, you know, this way. Let's denote its entries this way. So that's wn is equal to this, zn is equal to this. Sorry, zn is equal to this. I'm sorry. Xn is equal to this, and yn is gamma n, right? So gamma yn is gamma n. Okay, now wn being equal to this is greater or equal than 1, right? That's what I said here, right? I mean, here somehow cancel this one here and pass the 1 to the left, right? And you obtain you would obtain in that case this inequality, and then when you do the same thing but here, you obtain this inequality. Okay, and then the other inequality you obtain from here. I mean, again, passing the 1 here, right? Because this would be this. All right. Yeah, and this would be you see this. And here again, the 1 to the other side. Okay, so we have this inequality. Now, all of these matrices are in SL2R. I mean, these ones are obviously in SL2R, but the matrices, these ones I took in G, which was assumed to be a subgroup of SL2R. So all of these are in SL2R, so the determinant of Bn is equal to 1, which means, you see, that this times this minus this times this is equal to 1, so we can solve for xn this way. And then, well, of course, yn is gamma n. And one of the things we can see is that this is positive, well, greater or equal than 0, right? Because gamma n is positive, and this one is greater or equal than 0 because of these two inequalities. Okay, so it's greater or equal than 0. All right. Now we have this inequality. This you see both this one and this one are less than this number, so their product is less than the square of this one, right? I mean, yeah. Okay, so develop the product, right? And then you see pass 1 to the left and divide by gamma n, and what you obtain is that this xn is less than this number, right? And from this we see that that this sequence is actually bounded, right? So what we obtain is, actually you see from here, when we let n tends to infinity, actually what we see is that WNZN tend to 1 actually. But from here we can't quite say anything about the convergence of the xn's, right? Just that each xn is between 0 and 2 beta, so we don't quite know something concrete about the convergence of xn. We do know something concrete about the convergence of yn, so tends to 0. So here you see, here we know that this one goes to 1, goes to 0, but here we don't quite know. But we do know that it is bounded, right? Right, because for any given n, we have this, right? And the sequence of gamma n's is bounded. Okay. So you see this the sequence of bn's is then a bounded sequence in R to the 4th, let's say, right? And in R 2 times 2. So it has a convergence of sequence. Okay. So we have this sequence of elements of this discrete group, which would be convergent. So you see then it has to be stationary because of the discreteness of this group. Okay, so it's stationary, but then it's eventually constant. That's what it means. But so this one converges to 0, so it's eventually constant equal to 0. So the gamma n's are eventually constant equal to 0, contrary to this assumption, right? So what must happen? Well, our assumption that such sequence exists, with the lower left entries accumulating in 0, it must not exist. That's what must be happening. That is, that our lemma must indeed be true. Yeah, that's what we should be concluding. Okay, and so that's it for today's class. And tomorrow we are going to apply these results to obtain certain finiteness property of certain of the gamma translates of certain subsets of H related to let's say 6 points of elements of gamma, if you will. Namely, that if we have a locally finite fundamental domain and sets of certain forms related to fixed points of elements of gamma, then the closure of the locally finite fundamental domain intersects, has non-empty intersection with only finitely many gamma images of such sets of those shapes or forms. Right? Okay.